I met him actually last month at CVPR, where he gave a very interesting talk, and I thought it would be great if he shares some of his work with us here at Google. And just to spell his full name, so it's Hamed Masnadi-Shirazi, and he works at, or is in the middle of his PhD at UC San Diego with Nuno in the Department for Statistical Visual Computing. And yeah, I'm very pleased to hear about on the design of base-consistent loss functions for classification. So Hamed, please.
So thank you for the introduction. Yeah, so the title is on the design of base-consistent loss functions for classification. And this is work that I've done at the Statistical Visual Computing Lab at the University of California, San Diego. So during this talk, we're going to basically be talking about classification. Many classification algorithms, some of the most successful ones, such as SVMs and boosting, are basically based on minimizing the expected value of a loss function phi, which is
Excuse me, can you
both
focus on the
margin
slide?
enforcing and base consistent. So
Hello?
such loss functions assign a large penalty
Hello?
to points with a negative margin.
Thank you.
And they generally assign a small penalty to points of small positive margin and 0 or close to 0 penalty to points of large positive margin. So we also need to talk about base-consistent loss functions. And like I said, base-consistent loss functions are very special and important for classification. And the reason for that is because they produce the Bayes optimal decision rule without having to know anything about the distribution of the data. So an example for a general Bayes consistent loss function phi, we would take the expected loss to find the risk, and we would minimize the risk to find our predictor f star. And given that our loss function was Bayes consistent, we're guaranteed that f star, our predictor, is Bayes optimal. It implements the Bayes decision rule. And you can see that through this progression, we didn't make any assumptions about the model of the data. We didn't know the distribution of the data, nothing like that, but yet we were still able to arrive at the Bayes optimal decision rule. So on the other hand, unfortunately, only a handful of Bayes-consistent loss functions were previously known in the literature. Some examples include the well-known least squares loss that's used all over the place. Another example is the hinge loss that's used in SVM classifiers, or the exponential loss that's used in boosting. Another example is the log loss that's used in logistic regression and also in boosting. And you can see that each one of these previously known Bayes-consistent loss functions has led to a highly successful classification algorithm. We've plotted, actually, these Bayes-consistent loss functions, and just by looking at them, you can see that they all generally have a few properties in common. One is that they're all convex loss functions, and the ones that are considered here are all unbounded for large negative margins. And number 3 is that they all have 0 or close to 0 positive margins. Of course, this excludes the least squares that increases on both sides. And the last property is that they are all cost insensitive, meaning that they assign the same amount of loss to both the positive class and the negative class. So they don't prefer one class over the other. So the natural question that we could ask at this point is, are we stuck with just these 4 or 5 loss functions with those common shapes? And can we actually derive other Bayes-consistent loss functions that are custom tailored for our application? Can we derive Bayes-consistent loss functions that have other shapes and other properties? For example, can we have a Bayes-consistent loss function that's non-convex, like the plotted loss function? Can we have a loss function that's Bayes-consistent and yet has bounded negative margins? As you can see, this loss function flattens out. Can we have a loss function that has non-zero bounded positive margins, unlike previous loss functions? Can we have a loss function that's Bayes-consistent and is cost sensitive? So here we have two loss functions. One is assigned to the positive class, and the other is assigned to the negative class. And in general, can we have a Bayes-consistent loss function that's just any shape we want it to be, given our application? So these problems and questions were previously known, and researchers generally would try to start off with a known Bayes-consistent loss function, and in order to alter it to their application, they would either make alterations to the loss directly or alter the classification algorithm derived from the loss. And the problem with that is that once you actually alter the Bayes-consistent loss function in any way, it ceases to be Bayes-consistent. So during this talk, what we're going to show is how to actually derive novel Bayes-consistent loss functions. And this is work that has been covered in our NIPS 08 paper. We're also going to talk about designing novel loss functions, Bayes-consistent loss functions for specific applications. And two of the applications that we'll cover during this talk, the first one is going to be the designing loss functions that are robust or outlier resistant for robust classification. And this is work that's been covered in our CVPR 2010 paper. And we're also going to talk about designing loss functions that are Bayes consistent and cost sensitive. So this is work that's been covered in our ICML 2010 and IEEE PAMI 2010 papers. So now that we know the importance of having Bayes consistent loss functions for classification, we can talk about some specific problems and applications. An interesting problem is the computer vision problem. Here we have large margin loss functions generally don't overcome the unique challenges posed by computer vision problems. And one major difficulty is the prevalence of noise and outliers or class ambiguity that exists in computer vision data sets. So here, for example, we have an image of a famous street in San Francisco, and this is clearly an image of a street. But if we were to do patch-based image classification on this, we would get many patches that include trees and cars and building, even though this is supposed to be classified as an image of a street. So in order to be able to do robust classification, we're going to try to design a robust loss function. One limitation of current loss functions is their unbounded negative margin. So for this simple classification problem we have at the top, we clearly have three outliers. Those are the three x's, the green x's to the left are obviously outliers. And if we were to use the well-known exponential loss to classify this problem, the exponential loss has been plotted in light blue, the light blue dotted line. And because of its exponential shape, it basically will emphasize and concentrate on these three outliers and assign to them an exponentially high loss. Whereas what we'd really like it to do is to disregard these three outliers. So recent improvements have been made in terms of dealing with this type of outliers. One is the linearly growing logit loss used in logit boost introduced by Friedman in 2000. And that's the green line. You can see that it grows linearly instead of exponentially, so that's an improvement. The other is the bounded savage loss used in Savage Boost that we introduced in '08. And that's the dotted blue line in the bottom. You can see that it's actually bounded. It flattens out after a while. And so these help with these type of outliers. But we argue that the negative margins are not the entire problem, and that it's also important to penalize large positive margins. So in order to explain this further, we can consider this simple classification algorithm, this simple classification problem we have, where the data is distributed uniformly in the vertical direction and is Gaussian with equal variance and different means of +3 and -3 in the horizontal direction. So for these two classes, it's easy to see that the Bayes decision rule would be a line at x equals 0. And in fact, if any of the previous Bayes consistent loss functions are used on this exact data set, they would all place their decision boundaries where the red line is, which is very close to the black Bayes decision rule. So that all the previous Bayes consistent loss functions will approximate the Bayes decision rule almost exactly.
So you're getting Bayes decision rule by you know the underlying Gaussian?
I didn't get the question. What was that?
So you know the underlying Gaussian, so that's how you generate the Bayes decision rule.
The fact that I know that the optimal Bayes decision rule is the x line is because I know that they're Gaussian. But if all I had were these few points, and I used the Bayes consistent loss function, any one of these loss functions that I have on the right, they would actually, for this data set, give you the red line, which is almost on top of the black line, which is the optimal. So even if you didn't know anything about this distribution, and all I gave you were these few points, and you were to follow the procedure of start off with a Bayes consistent loss function, compute the risk, minimize the risk, you would get the red line without any information about the distribution. So that's the power of Bayes consistent loss functions.
But you're not assuming something about the data, which
I'm not assuming anything about the data whatsoever. All I have is just the data. I know that the blue lines is one class, and the blue circles is one class, and the red x's are another class. Given their coordinates, I can, but these points were actually sampled from a Gaussian, which I do not know whatsoever. Sure. And I'm going to actually consider what happens when you have a rogue point or something like that. It could actually change immediately. So what I'm going to do next is actually introduce an outlier here. So let's say I had one sample point at that point. So the impact of adding a single x at that point, which could still happen as part of the data, right? Because it's Gaussian in the horizontal, so that could be one of the x's that come out. The impact, but in essence, it is kind of an outlier for this data because it's highly unlikely. But in any case, if you do have a point at -2 and 0, what would happen is that all of these previous loss functions would drastically shift their decision boundary to where the purple line is. And they would place their decision boundary at about x equals -2.3. And the reason for that is because all of these loss functions assign 0 or close to 0 loss for being correct, right? This includes both the savage loss, which is the green one, or the log is the green one, and the savage is the blue one. So you can see that they assign 0 penalty for being correct And since by placing the line at negative 2.3, you can classify everything correctly, that's just where they're going to put their boundary, which is very far away from the Bayes optimal, had we known the true distribution. On the other hand, the tangent loss, which is a loss function that we're going to derive during this talk, is also Bayes consistent, but since it penalizes being correct, it penalizes both the positive side and the negative side. It discourages solutions that are too correct. So it'll actually place the decision boundary where the red line is, given this exact data, which is still very close to the Bayes decision rule. Yeah. No, I'm not assuming anything other than just the data. I mean, if... Yeah, that's true. If there was another, let's say another, let's say it was like two Gaussians, all of them made up the red class, that's true. That red point could be one sample from that. But the problem is that right now, given the fact that it's just one point, it's still considered kind of an outlier. I will actually deal with this problem later on because once you derive the tangent loss, you can actually change the amount that it penalizes being too correct. So you could even actually, flatten this to make it look like something like the Savage loss, which wouldn't penalize it, and actually place the decision boundary very close to where the purple one is. So you can have a control over this. It's just a matter of, given the data, it's right now, I mean, just looking at it, it would seem better to place the line somewhere close to the black one rather than drastically move it all the way to the left. Even if that were a distribution. And actually, when I was building this, toy example to get the point across of why it's important to sometimes penalize being correct, if you actually add another x to where that far left one is, the tangent loss will also place its boundary close to negative 2.3 because now it's, there's too much penalty for classifying 2 points wrong. And you would expect that if that was a true another mode, you would have more samples from it. And once you actually add another one, it'll shift. It'll be just too costly. It doesn't want to make a mistake on 2 points. So, yeah. But, I mean, this toy example is just to get across the importance of actually penalizing, outliers that are of this type. So you have to, in order to deal with these, you have to kind of penalize being too correct sometimes as well. So I don't know if I, yeah. Yeah.
So, I mean, it's an outlier in the sense that it's very unusual. It isn't an outlier in the sense that it's in error. So
Yeah.
philosophically, that is.
That's true. I mean, that's why you...
Samples from the world, and you would see enough street like that. So, in some sense, it's
Yeah.
hard to undersampling your.
That's true, but that's usually what we have to, I mean, that's what we deal with in the real world. We always have only a few samples. We never have the true distribution of the data. And so, I mean, the purpose of this talk is to say that it's important to have a Bayes consistent loss function that gives you that flexibility and that control. So when you are dealing with situations where you have small amounts of data and the possibility of having outliers is increased in that case, you want to be able to, have loss functions that are not only Bayes consistent, but also have, these different types of shapes that can deal with these potential problems.
So I think most SVM packages do another pass after you, and then they drop out outliers. But I don't think they would in this case because it's actually on the right side.
So I actually, if you were to use the hinge loss, which is what the SVM does, I didn't run an SVM because this is so simple you can solve it directly. You can just like do a exhaustive search over the space of lines here. But if you were to use the hinge loss, which is what the SVM uses, it does still place, because there's no penalty for being right. So why not place it where the purple one is?
Most SVM packages have a sort of, like they do optimize that, but then they have a fast drop out data, and you try and re-optimize something like that. I know that SVM might, but
Yeah, I didn't do a pass like that on this.
within this
So
case, that point's actually correctly classified. So
yeah. Uh-huh.
what the square loss have done, because it's sort of generalized, at least in your form, where you don't use a truncated square loss, it does what you would like to see.
The square loss. The square loss, the least squares loss, is actually almost never used in classification because, let me go back to its shape. That purple line, I'll give you a better example. So the red line is the square loss, right? And you can see that it penalizes being correct almost as much as it penalizes being wrong because of its symmetry. It's just x squared. So it's never used for classification. If I were to use, that's an interesting question. Maybe I should have used it here and see what would have happened if I had actually used the square loss, because then it would penalize this as well. And let's see, if it penalizes that point. So actually the square loss wouldn't work. It would place the line at where the purple is, I think. I'm kind of guessing, because there's going to be such a huge penalty for getting this wrong that it would prefer to get it right rather than skip over it. So the tangent loss here assigns a bounded penalty for being right. That's why it can disregard this outlier. You see that it tapers off here, right? It's bounded in that. Whereas the square loss would go up and would assign a huge loss for any incorrectly classified points of that sense.
Does this loss not encourage points to be near the boundary? You can pay a smaller loss when you're closer to zero.
Yeah. So exactly. That's the whole point of a loss like this, because it wants to, it wants to actually, in the paper, I actually have an example where I've plotted like a histogram of the distance. This is kind of the margin. So it actually encourages small margins that are placed at that place. I think it's that dip, that minimum is at like 0.5. But the interesting thing is that when you see that example, even though most of the points have a small margin of about 0.5, meaning that that minimum is actually enforced, it does better in classifying a data set that has lots of outliers. So I think in that example, we had some digit classification problem. And the margin is smaller, but the classification output is better than all of these other loss functions. So that's a problem that we actually considered in the paper. So it's just because the margin is smaller doesn't necessarily mean you're doing worse, especially when you have outliers. So that's true. It's just how much, for example, when you're using the exponential loss, it tries so hard to increase the margin that it, screws up the classification, which is the goal. So. I wanted to give these, I know what you're saying, But that's regression. It's not classification, because in regression, in classification, you actually have the two classes, and you're trying to minimize the risk. And in regression, yeah, if you allowed it to, plot a line through here, that would happen. It would place a horizontal line. So
If you penalize correct and incorrect in the same way, aren't you basically doing regression here? Because there's no cost, there's no different cost for being on either side of the line, only cost for being apart. So it is regression.
what I think I did for this data set was let's see. I think I limited maybe I didn't want that to happen, so I limited to vertical lines. That might have been what I did. So if I remember correctly, that's probably what I did to avoid that. In any case, I haven't even considered the least squares. So anyway, yeah. I think what I considered was like from -10 to +10, something like that.
So why do we have the second dimension actually? Why do we have in this example right there divided?
I wanted to put a y dimension here just so it would look nice when I plot it. Because if I only had that's why they're uniform in the y direction. So I already know that the y direction is, useless. Yeah. Because if I had only plotted these points in the x direction, you would get these circles on top of each other. You couldn't really see anything. But that's why I said it's uniform in the vertical, so you can disregard it completely. Yeah. But the point of this toy problem is something completely different. You guys should let me go further. What I wanted to just get across was the idea of the fact that first of all, we have problems where we have outliers. And second of all, we want to deal with outliers. And there's two types of outliers in a sense. One is when you're wrong. And so one is these type of outliers that I considered here, right? And the other is that when you can be actually right, completely right, and still have, an outlier. So the savage and the log kind of deal with the first type, but you also want a loss that looks like this that can, penalize being too correct, right? When you have outliers, that's just to get across the point of having a loss function that has a shape like this. Now, of course, we'll go into more, advanced and practical examples, so don't worry. But in order to derive something like the tangent loss that I just talked about, we need to talk a bit about risk minimization. So we define a feature x and the class label y, and we call our classifier h and our predictor f. So our classifier is just going to be the sign of our predictor f. And we also have the loss function L. And so what we're going to be doing is minimizing the risk or the expected loss, which is equivalent to minimizing the conditional risk. And here we're going to define eta to be the probability of one given x. So with these in mind, we'll consider the traditional approach of dealing with a Bayes consistent loss function. We're going to actually talk about what does Bayes consistency mean in more detail. So a good example is the exponential loss that we have here. And the traditional approach is to, of course, take the take the expectation, find the risk, C, and then you want to minimize the risk and find your predictor, F star. And for the exponential, you can actually show that F star will be 1/2 log of the probability ratio. So the question now is to see whether our predictor is Bayes consistent. And we've plotted this F star. And you can see that it is indeed Bayes consistent because it assigns positive values to probabilities that are higher than 1/2 and negative values to probabilities eta that are less than 1/2. So it's implementing the Bayes decision rule, which is good. So we're good there. We take our F star and we plug it back into our risk to find our minimum risk, which we call C star. And then what we have to do here is check to see whether C star is convex or not. And the reason for that is because it can be shown that in order to have a convex optimization problem, you need to have a minimum conditional risk C star that's convex. So for the exponential loss, everything works out fine. But you can immediately see from this example that this traditional approach doesn't actually let you design Bayes consistent loss functions. It only lets you check to see whether a loss function is Bayes consistent or not. And we can kind of say that we got lucky with the exponential because all these things, fall into place. So in our next section, we'd like to talk about how can we actually, we're going to propose a new path for designing Bayes consistent loss functions. And the general approach is going to be that we can choose any strictly concave function C star and any invertible function F star such that they have these simple symmetry constraints. And we plug these two functions into this formula and we get a phi, a loss that is guaranteed to be Bayes consistent. So this gives us a principled way of designing novel Bayes consistent loss functions. Now, I'm not going to actually go over the proof of that formula. The proof can be found in our NIPS 08 paper, and it basically deals with probability elicitation and Bregman divergences. And so I'm going to kind of skip over these, but we're going to go over an example of actually using the formula and deriving a novel Bayes consistent loss function. Here we're going to derive the Savage loss. So let's say we start off with the logistic link function that we actually saw in the exponential loss as well. And we pair it with the least squares minimum risk. And these two satisfy the symmetric constraints. All we have to do is take these and put them into the formula. And we derive a novel loss that we called the Savage loss. And we've plotted it. And you can see that this loss function, unlike all previous Bayes consistent loss functions, is first of all not convex. And also it is bounded. So it flattens out. It has a bounded penalty. And we use this loss function to do some robust classification. But for a truly robust loss function, we saw in our previous discussion that for a hypothetical loss, it should have a certain number of properties. We would, first of all, like it to be bounded for large negative margins. And we'd also like it to have a smaller bounded penalty, assign a smaller bounded penalty for large positive margins. And we'd also like it to be margin enforcing, of course. And it can be shown that under Bayes consistency, those three properties are satisfied if and only if these three conditions or requirements hold for our choice of F star and C star. And unfortunately, existing link functions F star don't comply with those requirements. So we introduced the tangent link, which does. So this is the plot of the tangent link. And we pair it up with the least squares at minimum conditional risk again, plug it into the formula, and we get what we call the tangent loss, which actually has the desired shape, of course. So now that we have our loss function, we can easily use it to do classification and derive, like, for example, a boosting algorithm to minimize the risk associated with this loss. I'm not going to go over deriving the boosting and algorithm and stuff. The details can be found in the paper. I'll just go over some examples and experiments that we did. We've done experiments on image classification and also multiple instance learning data sets. But here I'm going to talk about the scene classification, the 15-class scene classification problem. We used the semantic space representation from Rasiwasia and Vasconcelos CVPR 09. And the only thing that we changed was replace the SVM classifier with the tangent loss classifier. And we got 4. Now, their scene classification method was already state of the art, but we got 4% improvement with just simply, an outlier resistant to a robust classifier instead of the SVM. So, and actually, the interesting thing about this data set is that most of the improvements were seen between classes that were, I'm starting to lose my voice. What was that? Yeah, we're doing one versus all. The most improvement was seen in between classes that are easily confusable. For example, when you're trying to distinguish between the highway class or the street class or the tall building class, or when you're trying to distinguish between the mountain and forest and open country class. These are actually these are some of the 15 classes out there. There's also living room and bedroom and kitchen, and these are similar, but they actually produce the most improvements, which is expected when you're doing robust classification. We've also done experiments on tracking, and we used the discriminant saliency tracker of Mahadevan and Vasconcelos CVPR 09, and we used tangent boost to combine the saliency maps in a discriminant manner. Here in these two examples, tracking examples, the red box is for when the tangent loss is used to do tracking, and the dotted blue is when the exponential loss, which isn't robust, is used. This one, let's see if it works. No, it still doesn't work on my computer. That's weird. But okay, this one should work. So you can see that the tangent loss keeps track of the object, whereas the exponential loss drifts off and loses track. And this is because the person keeps changing shape, and there are plenty of outliers. So it's much more robust. Now, a natural question that was already kind of asked was, can we control the shape of the tangent loss? So there is actually a parameter A that controls the ratio between the negative margin and positive margin. So the general formula includes the A, and we've plotted the tangent loss for different values of A. And you can see that you can actually best results are found through cross-validation for A, or you can kind of like guess A depending on how much outliers you expect to have in your data. But in general, you can control the amount of penalty that you assign to the different margins. So you have that flexibility. Another question is the question of convexity. So here we have examples of a convex function, a quasi-convex function, and a function that's neither convex nor quasi-convex. And so for a quasi-convex function isn't convex, but it still has a unique minimum. On the other hand, all convex functions are also quasi-convex. And we can actually prove that base-consistent loss functions from this formula are all quasi-convex. Now, the main question is our optimization problem still convex even when the loss is not convex? So so the thing to keep in mind here is that we're not minimizing the loss, we're minimizing the expected loss or the risk. So with that in mind, we can prove that the risk is actually still convex in probability space, even though the loss is not. We can also prove that the risk is quasi-convex in functional space. And this is an important proof because when you're doing classification, you're usually not working in probability space. You're working directly in the functional space. You're trying to directly find the function that classifies, that minimizes your risk. So it's still quasi-convex, even though the loss is not. And also, more importantly for practice, the empirical risk is also quasi-convex in functional space. So in conclusion, we can say that the optimization problem is quasi-convex and has a unique minimum that can be found with functional gradient descent, such as boosting, even though the loss function is not necessarily convex. So the optimization is not, by definition, convex, but it's quasi-convex, meaning that it still has a unique minimum. So you can use quasi-convex methods to find the minimum. The easiest thing that works is just do functional gradient descent, which is what boosting does. That's why the boosting algorithms work, even though these loss functions have all these, quasi-convex shapes. So the important thing is that it still has a unique minimum.
But normally you minimize the sum of the losses, so you're going to have actually a function, although I agree it's got a unique minimum, it's going to be many potentially local.
No, that's what I mean by unique minimum. It doesn't have local minima. Even the empirical risk won't have local minima. That's what's. Well, I can actually prove this, if you want later. Initially, that's the question that people have. They think that, since you have a bunch of these little dips for these different points. But think of it this way. Let's say you only had 1 point, and you're trying to do like the worst case would be to just have like 1 or 2 points. You can still show that the sum of 2 quasi-convex functions that have this formula are themselves quasi-convex, meaning that the sum of even 2, like the simplest classification problem in the world is just 1 point here and 1 point there, right? The sum of these 2 would still be another quasi-convex function. That's the empirical risk, right? The sum of 2 of these losses. Let's say you sum 2 of those. Yep. You can sum any 2, and they'll still be quasi-convex, as long as they come from this formula. Maybe I should have. But the thing is that before giving, I got this question during my CVPR talk, and I had gotten the first question when I gave the NIPS paper. So I knew I was good in terms of probability space, but that's not the space we really are dealing with. Because when you do a transition from the probability space, a transform doesn't necessarily preserve convexity. So when you transform from the probability space into functional space, there's a chance that you'll lose convexity. And so I had to actually go and prove 2 and 3 as well, which that's why I wanted 2 weeks before I came to give this talk, because I spent the first week actually proving 2 and 3. It's actually quite simple to do. If you take the derivative of this function down here, you can prove that it's quasi-convex by the classic way of proving quasi-convexity, which is to show that the derivative is positive up to a certain point, and then negative from then on, meaning that there's only one change. That's the general, one of the ways to prove quasi-convexity. So, yeah, so the sum, adds a little bit more, but it's still nothing more than adding one function phi of v plus, let's say, alpha times phi of negative v, which is the positive class plus the negative class. So, and in fact, once you prove 2, 3, which is the case that you're talking about, is not that bad afterwards. So we can go over it. Yeah, maybe that's what I should have concentrated on more later. Yeah. This I haven't actually included in any of the papers. Part 1 is in the NIPS paper, Theorem 1, but 2 and 3 were added to the paper that like the journal version of the paper that I'm writing, and it's almost done. This is kind of like the missing link. So. No, just any. I just gave the simple 2 example. But the point is that you can add alpha number of the positive numbers and beta number of negatives and still have a sum. So the thing about convexity is that when they're talking about empirical risk, we all know that the sum of a bunch of convex functions is still going to be convex. And that's why when you're doing empirical risk minimization, using convex loss functions, the thing works well, because you know that when you sum up a bunch of convex functions, you're still going to have convexity. The same theorem, unfortunately, doesn't exist for quasi-convex functions in general. You can't say just summing up a bunch of quasi-convex functions will ensure convexity. But fortunately, if they come from this formula, they do. So the sigmoid is almost like savage, but it's not exactly. It's not one of these. I'm trying to find the formula for savage. Here it is. It looks almost like the savage, but it's not exactly. The savage does too. I mean, it's quasi-convex. It's derived from that formula. It'll still work. But yeah, it seems more remarkable that you would have a loss function looking like that. That would still work, but so are we? So I can move on, hopefully. Okay, so in conclusion for this section, we showed how to derive novel Bayes-consistent loss functions for classification, and we derived a set of requirements that a robust Bayes-consistent loss function should have. And we also showed that Bayes-consistent loss functions can be non-convex. And we gave some examples of using the tangent loss function for doing classification. I don't know if we have enough time, but we can. I also wanted to talk about deriving Bayes-consistent loss functions that are cost-sensitive. So I've been talking for about 50 minutes already. Do you want me to continue? Or? Okay. So many classification problems are actually naturally cost-sensitive. For example, when we're doing detection or fraud detection or medical diagnosis or business decision-making, the cost of one misclassifying one class is usually much higher than the other. So for medical diagnosis, for example, missing a tumor might be considered as having an infinite amount of loss because it might result in the death of a patient. Whereas on the other hand, a false alarm or a false positive would just cost a bit more money because you have to do further experiments. So there's obviously a demand for cost-sensitive extensions of state-of-the-art techniques. And here we propose an alternative strategy for the design of cost-sensitive algorithms. Rather than directly manipulating the algorithm and risk compromising Bayes consistency or Bayes optimality, we extend the underlying loss function and derive a cost-sensitive learning algorithm from that loss that implements the Bayes decision rule and also approximates the Bayes risk. So here, this is just the same slide that we had before to remind us of the general path that we took before for deriving Bayes consistent loss functions. We would choose any strictly concave function f star and c star. Sorry, strictly concave function c star and invertible function f star, such that they satisfy these constraints. We'd plug it into the formula, and we were guaranteed to have a Bayes consistent loss function. And the question now is, can we have a general procedure for deriving cost-sensitive loss functions as well? So here we're going to define C1 as the cost of a false negative and C negative 1 as the cost of a false positive. And we'd like to ask what conditions need our choice of F star and C star now satisfy, such that we have a cost-sensitive loss that's also Bayes consistent. So generally we would have a loss phi1 assigned to the positive class and the loss phi negative 1 assigned to the negative class, but we'd still want to conserve Bayes consistency. So the generic procedure is to start from an invertible predictor f star that has this symmetry, and a concave function c star that has this symmetry. And this symmetry is basically the same symmetry that the Bayes risk have. So we're ideally trying to find a risk that has the same behavior as the Bayes risk. And then we define J to be negative of our C star. And we derive these auxiliary functions I1 and I negative 1 from these two formulas. And our loss functions can be shown to basically be the negative of I1. So phi1 is going to be negative I1, and phi negative 1 is going to be negative I negative 1. And these come from probability elicitation. The proof comes from there. But in general, the theorem is that the loss derived through this procedure is cost-sensitive and Bayes consistent. So here we're going to go over an example, which would be the exponential. We're going to try to derive the exponential cost-sensitive loss. We choose f star to be this formula, which is the cost-sensitive version of the log link. And you can see that it is cost-sensitive. It implements the cost-sensitive Bayes decision rule, because now the boundary has shifted from a half to, in this case, 0.3, because C1 was chosen to be 2. So all points that have probabilities higher than 0.3 are now assigned positive values, and all points that have probability less than 0.3 are assigned negative values. So we've shifted the boundary to make it, to prefer one class. And we also have the cost-sensitive version of the risk. And you can see that in this, it's still concave, but it has an asymmetric shape. And the point here is that the maximum of this risk is, again, at 0.3. So the maximum risk is being assigned to the boundary, which is what we want. going through all the steps, we can find phi1 to be like this, which is now the cost-sensitive version. And there are now two loss functions. One is the red one that's used for the negative class, and the blue one is the loss that's used for the positive class. And it's still base consistent. So we've actually used the...
Those now capable have combined the properties that we had earlier of this penalizing too large positive margins. So do something like a tangent loss and still make it cost sensitive, or that's still asking.
You could, I haven't, in order to get a loss function that looked different, you would have to choose different F stars and C stars. So if you could go back and derive the cost-sensitive asymmetric version of the, well, you already have it here. Combine it with the cost-sensitive tangent link, you could probably get an analogous version for the cost-sensitive one. I haven't done it, but maybe that's up for grabs. Yeah, so the least squares is the same C star that's used in tangent. The difference here is that the tangent uses a different F star. So if you derive the cost-sensitive version of that one, you could get something similar. But here we use just the exponential. And the reason for that was because the history of this is because I wanted to derive the cost-sensitive version of AdaBoost. And that uses the exponential loss. But here, using the cost-sensitive version and still base consistent boosting, we've done a lot of experiments for pedestrian and car and face detection. We've even used it for brain EEG, surprise signal detection. But I'm going to move on to deriving the cost-sensitive SVM. Yeah. So there have been lots of papers on making AdaBoost cost sensitive. In the PAMI paper, that's basically what it's all about, is going through the history of this and finally, deriving this, which is the cost. And the interesting thing about this is that it's still base consistent. All of the previous methods usually dealt with altering the AdaBoost algorithm directly. What they would generally do is change the weights. So the AdaBoost has this weight update formula. They would go introduce costs directly to the weights. And depending on how you kind of change the weights, you would get different algorithms. But when you go and alter the algorithm like that, you have to still kind of show that it's base consistent, because otherwise you don't know what you're doing anymore. Are you really minimizing, what you should be? And given infinite amount of data, will you still converge to the Bayes decision rule, which is what you should be doing? So here, when you show that it's base consistent, you answer those problems. And you don't need to go directly manipulate the algorithm. Once you have the correct loss, you can just derive the classifier from it. And that's what we did. So we're going to try to do the same thing for the SVM, because there have been many papers on cost-sensitive SVMs. But again, what they would do is, go into the algorithm and, tweak this or change that portion or add a cost here or there. But the principled way to do it is to actually derive the cost-sensitive loss function, show that it's base consistent, and then once you have that, the rest is just, go through the steps of finding the algorithm. So here we're we're going to start with f. We're going to choose our f star to be this, which can be shown to be Bayes consistent, and it implements the Bayes decision rule. And in fact, it's just the cost-sensitive version of the link used in SVM. So if you set C1 and C2, if you set, C1 and C negative 1 equal to 1, it will just, simplify to sine of 2 eta minus 1, which is the exact same thing used in SVMs. So for cost-sensitive, so this suggests the cost-sensitive minimal conditional risk. And this has 4 parameters A, B, D, and E that can be shown to satisfy the symmetric conditions for Bayes consistency if they satisfy these conditions. But in any case, if you go through the steps, you can find the cost-sensitive SVM loss function, which is what I have there. So this loss has 4 degrees of freedom, A, B, E, and D. And for the positive samples, we've classified, basically they're assigned a margin of E over D and the hinge slope of D. So if the red line is the positive hinge loss, they get a slope of D and a margin of ED. For the negative, you have a margin of B over A and a hinge slope of A. So the blue line is the hinge loss that's used for the negative samples. And after some parameter normalization, you can find C star to be like this. But you go through the steps, and now that you have the loss, the risk basically leads to the cost-sensitive SVM primal formulation. And this is assuming that you're preferring the positive class. You can derive a similar primal formulation for equal to 1, which is a good check, right? Because if it doesn't return to the standard SVM when I set the cost equal to 1, I've probably done something wrong. But it does actually simplify to the standard SVM when you set the costs equal. But here we have some experiments that we've done using the cost-sensitive SVM, and we've compared it to the previous algorithms, the boundary movement SVM and the bias penalty SVM. So the bias penalty SVM would introduce costs on the slack variables directly, and the boundary movement SVM would basically just change the bias of your final SVM. So compared to these two competitors, that we did experiments on 10 UCI datasets, and cost-sensitive SVM has smaller error on 7 out of the 10 datasets and does equal to bias penalty on 2 other ones. We also did experiments on the German credit dataset, and here the goal is to identify bad credit customers to be denied credit by the bank. And each person gets 24 attributes, such as 24 features, such as the person's age and income. And we're trying to decide whether the bank should, give this person credit or not. The interesting thing is that here the cost matrix is actually defined in the problem, because if a good credit customer is denied credit, the bank has a loss of 1, meaning that the bank loses a good customer. Whereas if you give credit to a bad customer, the bank suffers a loss of 5, meaning that so the bank loses money. So this suggests the following constraint on our choice of C1 and C negative 1. The ratio should be 5, and this is defined in the problem, so it's part of the data set. But the final results is that if you use cost-sensitive SVM, you get a total reduction in cost of 37%. So in conclusion, we extended the problem.
Just go back 2 slides. So here, you're actually using the error rate, which doesn't take into account cost sensitivity. Is that right? Or is this actually fine loss?
So here is, no, there are different ways to compute the error. So here what we did was just count the number of errors that you have. over the data. There isn't any cost sensitivity incorporated within the data set itself, because I don't know how much a miss would cost when I'm doing, let's say, heart disease, or I'm trying to do PIMA. I wouldn't know. I mean, you can define these to be whatever you want. It wouldn't change the result. It would just be multiplying these by a number.
But I was wondering, yeah, so, I don't know, so you change the cost sensitive nature, so essentially you're going to make potentially more errors.
Yeah, so okay, so to go into details of how I actually did this, the way we did it was all of these algorithms have their different parameters, right? Like the C1, C-1. So we tried all the different parameters such that all of these algorithms attained a certain detection rate on a validation set. So for example, we said we want to have all of these such that they have 90% detection rate. Once they're equal on that sense, I would go to the test set and test it and see how many false positives they gave me. And of course, the one with the smallest false positive would be the best, because I've ensured that their detection rates are fixed, given the amount, like the amount of flexibility these have. The cost-sensitive and bias penalty SVMs, they have the same number of parameters that you can tweak. But the boundary movement SVM, the only thing you can change there is just the bias. So, but with that in mind, that's the fair way of comparing them. So for this section, we extended the probability elicitation view of loss function designed for cost-sensitive problems, and we specified the generic procedure for deriving cost-sensitive algorithms, and also derived the cost-sensitive Bayes consistent boosting in SVM loss functions, and also went over some experimental results. And thank you. So I'm open to any more questions.